becomes the numerator, and the divisor becomes the denominator. In other words, we read this as what? 3/4. 3 over 4. See, 3 divided by 4 is 3/4. 17 divided by 24, that's 17/24. And 5 divided by 6, that's 5/6. Now you see, once we have it in this form, now we go back and solve this problem just as we would have in self-test 4. Namely, to compare these, it's not enough to look at the numerators. We have to have a common denominator. I will spare you the details of finding common denominators because that was in the last exercise set. Probably by inspection, you notice that the least common denominator here was 24. 4 goes into 24 6 times. 3 times 6 is 18. 24 goes into 24 once. 17 times 1 is 17. 6 goes into 24 4 times. 5 times 4 is 20. So the three ratios are 18 24ths, 17 24ths, and 20 24ths. And when the denominations are the same, the greater numerator names the greater number. So therefore, since this is the greater numerator, this is the greater fraction, and therefore 5/6 is the biggest ratio. And what I wanted to comment on over here is don't be deceived by what things look like. A lot of times people look at these numbers and they say, gee, 5 and 6 are pretty small compared with 17 and 24. Well, sure, 17 and 24 are big numbers, but keep in mind what this is really saying. This is saying you're taking 17 out of every 24. Here you're taking what? 5 out of every 6. And that's the same as taking 20 out of every 24. Now the question is, if we can do this kind of a problem, where do we use it in real life? And in real life, whenever you divide one number by another, remember that numbers are adjectives modifying nouns. When you divide two nouns, you're finding a rate. And a very common type of rate is known as the unit price. And that's what I want to show you in the next problem. The next problem says, which of the following is the cheapest price? You can buy 40 pounds for $25.20, 30 pounds for $19.50, and 50 pounds for $30.50. I suspect when I copied this down, I left out an important piece of information. Because if you take this problem literally, the cheapest price is B. It says, which is the cheapest price? Well, of these three prices, obviously $19.50 is cheaper than the other two. I suspect the problem was worded, which of the following represents the cheapest price per pound? That's the way I'm going to solve the problem anyway. So, in other words, if I want to find the price per pound, I can measure the price either in dollars or in cents. I prefer to use cents at this stage of the course because if I use dollars, I'm concerned with a decimal point, and technically speaking, we don't handle decimals in this course until the 7th module. So here's the idea. See, we're going to deal with dollars or cents per pound, and the key step in a ratio problem is that per can always be replaced by a division symbol. So in terms of part A, the number of dollars is $25.20, which we can call 2,520 cents. And the number of pounds, see, in other words, in cents, this is 2,520. And the number of pounds here was 40. So we have this division problem. 40 goes into 2,520. Well, 40 goes into 252 6 times. 6 times 40 is 240. We subtract, we get 12. Bring down the 0. 40 goes into 123 times. No remainder. Therefore, the first rate comes out to be 63 cents a pound. See, that would be called the unit price. That's the unit price. Let's see the unit price. See, the unit in this case is a pound. Let's find the unit price in the second case. The second case, we're paying $19.50. That's 1,950 cents, but for 30 pounds. So that's going to be what? 1950 divided by 30, which as a Gazinta problem says 30 goes into 1,950. So we just do the long division here. 30 goes into 195 6 times. 6 times 30 is 180. 180 from 195 is 15. We bring down the 0. 30 goes into 150 5 times. So this comes out to be 65 cents a pound. By the way, let me just pause here for a moment to point out to you that a moment ago we showed that B was the cheapest price for the whole amount. But per pound, you see, it was only $19.50, but you were also getting what? the least number of pounds, or a smaller number of pounds for that amount. And so price per pound, that was a pretty high price. See? And I just want to point that out to you. Notice the difference between the total price and the price per pound. In fact, while I'm expounding this way, aren't there times when you might want to buy the cheapest package, even though it may not be the best unit price? For example, if you know that at dessert time in the house, the kids are going to eat whatever amount of ice cream you put down, whether it's a pint or a gallon. You see, even if the gallon is a better unit price than the pint, and all you want to do is make sure they all get some ice cream, you give them the pint, which is much cheaper than the gallon, and that's the cheapest dessert, even though if you had used 8 pints at that price, it might have been very expensive as opposed to buying 2 gallons. So keep that in mind also. Okay? At any rate, let's go back to Part C. In Part C, you're paying $30.50, which is 3,050 cents, but you're getting 50 pounds. 50 goes into 3,050. Let's see. 50 goes into 305 6 times. 6 times 50 is 300. We subtract, bring down the 0. 50 goes into 50 once. So the third price is 61 cents per pound. So of these 3 prices, A was what? 63 cents a pound. B was 65 cents a pound. C was 61 cents a pound. So the best price is C. The best price is C. And by the way, does that mean that you're going to buy C? Again, I want to remind you as you're doing these problems, don't lose sight of the whole picture. If all you care about is price, yes, C is the best deal. But is it possible that A or B is a brand that you prefer? Is it possible that the store that charges prices A or B is 20 miles closer to your home and you're going to spend in gas more than the savings are worth? See, all of these thoughts have to go into the decision making. All the mathematics did was it told us the cheapest price. And one more admonition. Dollars per pound is not the same as pounds per dollar. In other words, if you reverse the order, you don't find dollars per pound, you find pounds per dollar. How many pounds you can buy for $1. This is tricky. You see, the more pounds you can buy for $1, the cheaper the price is. You see, $4 a price is cheaper than $4 a pound is a cheaper price than $5 a pound. Okay? But 4 pounds for $1 is more expensive than 5 pounds for $1. See, the more you can get for the same amount, the less the price is per pound. So if you do these things in reverse, make sure you know how to interpret the problem. See, the only thing worse than the wrong answer to the right problem is the right answer to the wrong problem. And that's going to become a theme, especially when we get to Module 9 and are allowed to use the calculator. But let's go on with these problems now. Problem number 3 is also designed to help make sure that we understand what we're doing. Mechanically, all the problem says is, how much is 4/13 times 5/9? And how do we multiply 2 fractions? We multiply the numerators and multiply the denominators. By the way, I don't suggest that you always do this, but many times we prefer the answer in lowest terms. And if you're going to do that, what I tend to like to do here is, especially if it's not too hard, before I do the actual multiplication, I do an extra step. And I write both numerator and denominator in terms of prime factors. See, I rewrite the numerator as 2 times 2 times 5. The denominator is 13 times 3 times 3. And now I notice that there is no common prime factor of the numerator and denominator. That tells me this is already in lowest terms. So now I multiply and I get what? 20 over 117. That's the mechanical answer, but what does it mean? And all it means is that if you're keeping 4/13 of 5/9 of an amount, you're keeping 20 out of every 117. And to visualize this, since 117 is the least common multiple of 13 and 9, let's actually compute how much we'd have if we took 4/13 of 5/9. Okay, let's use the amount as being 117. You see, 1/9 of 17 is 13. And 13 times 5 would be 65. See, and get a feeling for what this thing really says. It says at a rate of 5 out of every 9, you would be taking 65 out of every 117. So if you started with 117, all you're keeping is 65. What's happening to that 65? You're now only going to keep 4/13 of that. So at a rate of 4 out of every 13, how many do you keep out of 65? Well, you see, there are 5 13s in 65, so you're going to keep 4 5 times. You see, 65 divided by 13 is 5. 5 times 4 is 20. So how many did you keep altogether? 20. How many did you start with altogether? Be careful, not the 65. That was after you already took a portion. What you started with was 117. And therefore, can you see now what the meaning of Part A is? Do you see what problem you've solved that way? Now, Part B is designed to warn you, please read carefully. See, Part B looks an awful lot like Part A, especially if you read incorrectly. Part B says, by what must you multiply 4 13ths to get 5 9ths? And if you read that very quickly, all you see is what? The 4 13ths, the 5 9ths, and the word multiply. And most people who are careless, when they see Part B, wind up doing Part A. See, be careful what this thing says. It says, what number, that's the unknown, must you multiply by 4 13ths to get 5 9ths for the answer? And by the way, let's construct that. Remember how we did that in the lecture? We want to wind up with 5 9ths. We have 4 13ths. To get rid of 4 13ths, we multiply by 13 over 4. That gives us 1 for the product. And 1 times 5 9ths is 5 9ths. So altogether, we multiply by what? 5 9ths times 13 fourths. 5 times 13 is 65. 9 times 4 is 36. So the answer is what? 65 over 36. And how can we check that? If this is right, what should happen? If we multiply the answer by 4 13ths, we should get 5 9ths. And look what happens here. 13 goes into 65 once, 4 goes into 36 9 times, and the answer, lo and behold, is 5 9ths. Notice that mechanically, when we divided, well, let me just come back to that in a moment, and we'll just go on this way. The way I did this problem actually is how you prove the formula for dividing 2 fractions. See, basically, when you see blank times 4 13ths equals 5 9ths, that looks like a multiplication problem. But since one of the factors is missing, it's really a division problem. In other words, when you see this problem, how are you supposed to read it? Parentheses equals 5 9ths divided by 4 13ths. And how do you divide? You leave the first number alone, change the division to a times, and invert the second. And what do you wind up if you get that? 5 9ths times 13 fourths. And do you notice over here? That's exactly what I got doing it the other way. 5 9ths times 13 fourths. See, we invert the second because it gives us the right answer. If mechanically you inverted the first, or if you inverted both, you would get a different answer, but it would be wrong. And why would it be wrong? Because if you checked out what properties it was supposed to have, it wouldn't have that property. Remember, whatever the right answer is, 4 13ths of it has to equal 5 9ths. And we'll show how that's applied a little bit later on. I did want to show you, however, a way, in case you get confused, as to know whether when you have this, do you write it as 4 13ths divided by 5 9ths, or do you write it as 5 9ths divided by 4 13ths? How do you know this is the right way of doing it? And I thought that I would like to show you a little trick just to help you. You see, putting in fractions just makes this more complicated than if we had used whole numbers. But whole numbers are less confusing. So let's suppose we call this the first number, f, and s for the second number. See, f and s. So this is the first number. See the number on the left of the parentheses, and on the left of the equal sign. Let s be the second number. Now, in this problem, what's the right answer? Parentheses times 2 equals 6. We know the answer is 3. How did you get the right answer? Did you divide 2 by 6, or did you divide 6 by 2? You divided 6 by 2. That's easy. Now go back and see what 6 divided by 2 says. 6 divided by 2 is the second divided by the first. Therefore, the same structure is going to hold in the fraction case. Go back to the fraction case. Second divided by the first is 5 9ths divided by 4 13ths. Remember, if you reverse this problem and do 4 13ths divided by 5 9ths, you will get the reciprocal of the answer, not the answer itself. But you can check that out just to see how this thing works. Okay? And we're going to continue on this way, seeing how multiplication works. Here's an example. which is greater and by how much? You have a choice between taking 2/5 of 3/7 or 3/10 of 5/14. Well, this starts to get heavy to juggle in your head. I'm taking 3/7 and I'm taking 2/5 of that. On the other hand, I can take 5/14 and then take 3/10 of that. The trick is, don't worry about that. Of means times. And when you multiply two fractions, you multiply numerators and you multiply denominators. So what is 2/5 of 3/7? Of means times. 2 times 3 is 6. 5 times 7 is 35. So 2/5 of 3/7 is the same as 6 out of every 35. On the other hand, what's 3/10 of 5/14? 3/10 of 5/14, okay, that's what? 3 times 5 is 15. 10 times 14 is 140. So 3/10 of 5/14 is 15 over 140. By the way, did you notice that that could be written in lower terms? See, 15 ends in a 5, 40 ends in a 0, so both numerator and denominator are evidently divisible by 5. Well, see, we could have done that here. See, the 5 in the numerator cancels with the 10 in the denominator to leave a 2, okay? And we're left with what? 3 over 28. So you can do the problem that way if you want to. At any rate, though, you see 6 over 35 is 6/35. 6/35 multiplying numerator and denominator by 4 is the same as 24 over 140. So now compare these two results. You see 6 over 35 is 24 over 140, okay? And 15 over 140 is only 15 over 140. So which is the greater one? This one. By how much is it greater? It's greater by what? 9 parts. 24 minus 15. 9 parts in 140. You could have reduced this thing first into lower terms. In other words, you could have reduced this, and now you'd have to compare what? 3/28 with 6/35, and you'd still have to find what? A common denominator. Notice that 28, I won't factor the 4 here, breaks down basically into 4 times 7. 35 breaks down into 5 times 7. So once I have the 4 times 7, all I need is the 5. So 4 times 7 is 28, times 5 is 140, and I get back to the same problem. And again, the thing I want you to notice over here is when you're dealing with fractions, you can't go by the actual sizes of the numerator and the denominator. See, 2 over 3 looks pretty small, but it says you're taking 2 parts out of every 3. 1 million over a billion looks very big, but it says you're only taking what? Out of every billion, you're only taking 1 million. That's a very small ratio, okay? Let's continue on this way and look for a few more practical examples. Problem number 5 says a recipe calls for 7/8 of a cup of sugar. You only want to make 2/3 of the recipe. How much sugar should you use? And by the way, just like some people try to avoid fractions in the real world, even if it gives them upward mobility, people will also do the same thing in using recipes if they're not good at math. Some people will say, well, what the heck? Why bother making 2/3 of the recipe? I'll make the whole recipe, and we'll just give out bigger portions, or I'll freeze what's not used. Other people say things like, well, I'll use the whole 7/8 of a cup of sugar, so it'll be a little sweeter, who cares? See, we have all sorts of rationalizations to get through in the real world. But suppose it was really mandatory to economize. For example, suppose you're cooking for an army, so to speak. And suppose the recipe calls for feeding 3,000 people, and you're only going to feed 2,000 people. What are you going to do, cook for the whole 3,000? I guess you could do that in certain places and just justify it as overhead. But for most people, you're really going to take what? The 2/3 of that amount. And I want to show you how easy that problem is if you're not afraid of fractions. You see, you want to make what? 2/3 of the recipe. So whatever ingredient is given, you're going to use 2/3 of that. You're only going to use 2 parts out of 3. Well, see, the part that's already used is what? 7/8 of a cup. Do you see the fractional part of the fractional part? The recipe already calls for a fractional part of a cup. And you're now going to take what? A fractional part of that. See, you're taking 2/3 of 7/8 of a cup. And how do you take 2/3 of 7/8? This is times. You can multiply numerators, multiply denominators. But I guess it's easier to reduce this thing first. 2 goes into 8 4 times. So the numerator would be 7. The denominator would be 12. So the answer would be what? 7/12 of a cup. that's how much you would use. 7/12 is what? 6/12 would be half. So the recipe says what? Just use a smidgen over a half a cup. And by the way, a small point, but a very important point. Notice that the correct answer to this problem is not 7/12. It's 7/12 of a cup. In the real world, unless the noun is given as part of the question, you have to put the noun in. See, if the problem says how many miles are you going, if you say 50, it's understood that the 50 is modifying miles. If the problem says how far did you go, you can't say 50, because it could be 50 feet, 50 kilometers. You've got to give the label. So since this problem said how much sugar should you use, the 7/12 by itself is not a complete answer. It's like a person says, what do you want to wear today? You say, I want to wear a yellow. See, you've got to give the noun also. So how much sugar? 7/12 of a cup. Not 7/12 tablespoons, not 7/12 ounces, 7/12 of a cup. Okay? Let's go on to more exciting things. Let's see what we have next. I forget what the problems are until I see them here. Number 6 says, your friend buys 2/5 of a carton of books. You buy 4/7 of what's left. What fractional part of the carton did you buy? And if you have any hang-ups about fractions, this is the kind of problem that's going to do you in. Look at how many places fractions appear in the wording of this problem. And I want to show you how you can solve this problem by thinking whole numbers. I will first do this problem for you in an intuitive way, well, a relatively intuitive way. For some things, there is no real intuitive way, and then I'll do it for you by the pure mathematics. See, method 1 says, when you're afraid of something, but not afraid of something else. If the two are related, think in terms of the thing you're not afraid of. Hopefully you're not afraid of whole numbers. So think whole numbers. Since we're talking about fifths and sevenths, we want a whole number that's divisible by both 5 and 7. And the easiest one to pick is what? 5 times 7, which is 35. So for the sake of argument, pretend there are 35 books in the carton. What does the problem say? The problem says your friend is buying 2/5 of the carton. 2/5 of the carton is 2/5 of 35 books. 35 divided by 5 is 7. 7 times 2 is 14. So your friend buys 14 books. Now you've got to be careful. Read the problem carefully. The problem says you buy 4/7, and watch the noun that's coming in now. 4/7 is just the adjective. You're buying 4/7 of what's left. You're not buying 4/7 of what he bought. You're buying 4/7 of what's left. Well, if he bought 14 and there were 35 to start with, how many are left? 35 minus 14, which is 21. What are you buying? You're buying 4/7 of the 21 books to the left. 21 goes into 7 goes into 21 3 times. 3 times 4 is 12. In other words, at a rate of 4 out of every 7, see, at a rate of 4 per 7, if this is still bothering you, notice that the rate of 4 per 7 is the same as a rate of what? 12 per 21. We've talked about that before. If you multiply both numbers in the rate by the same whole number, you don't change the rate. In other words, if you're counting by 4s, 12 is the third number you're coming to. If you're counting by 7s, 21 is the third number you're coming to. So you're buying what? 12 books. 12 books out of how many? 12 books out of the 35. Therefore, what fractional part of the carton did you buy? You bought 12 of the 35 books that made up the carton. You bought 12 35ths of the carton. Follow that problem okay? All right. See, now the other way to look at this, method 2, is you just think fractions. You just don't become afraid of anything. You just say, look, my friend bought 2/5 of the carton. So if there were 5/5 to begin with, if he bought 2/5, there are 3/5 left. I'm buying 4/7 of that 3/5. 4/7 of 3/5 is what? Of means times. 4 times 3 is 12. 7 times 5 is 35. There's the same 21 over 35. See, remember the key point is reading comprehension. If the friend buys 2/5, 3/5 is still left. And do you see the difference between this problem and an addition problem? An addition problem would say your friend buys 2/5 of a carton and you buy 3/7 of the carton. Between you, how much of the carton did you buy? Do you see the part of a part here? Your friend buys part of the carton, that leaves a part, and you buy part of what's left. See, keep that in mind. That's a very, very important concept here. Follow that very, very carefully. Make sure you understand that. Okay? And there's lots of other things we can talk about on this problem, but let's go on and make sure we get through the rest of the problems during this particular lecture. Next one is designed to show you that even for fractions, the distributive property for multiplication still holds true. Problem number 7 says, write each of the following as a common fraction in lowest terms. And see, part A says you're going to take 3/4 and multiply it by the sum of 2/3 and 4/7. You see what that says? The parentheses are grouping symbols. Part A says, first add, then multiply. Look at part B. Part B says, take the 3/4 and multiply it by the 2/3. Then take the 3/4 and multiply it by the 4/7. See the distributive property? Add the two together, and let's see what answer we get. And you see, if the distributive property is correct, these two answers should come out to be the same. So let's do that. See, for part A, first of all, 2/3 and 4/7. The common denominator is 21. So 2/3 is the same as 14 over 21. See, multiply numerator and denominator of 2/3 by 7. 4/7 is the same as 12 over 21. So you just multiply numerator and denominator of 4/7 by 3. 14 over 21 plus 12 over 21 is 26 over 21. So now I'm taking the 3/4 and multiplying that by 26 over 21. That gives me 78 over 84. Problem was supposed to be in lowest terms. How do I know this isn't lowest terms? Well, because this ends in an 8, this ends in a 4. They're both divisible by 2. Secondly, 7 plus 8 is 15. 15 is divisible by 3. 8 plus 4 is 12. 12 is divisible by 3. 15 is divisible by 3. So in other words, if a number is divisible by both 2 and 3, it's divisible by 6. If I divide 6 into 78, I get 13. If I divide 6 into 84, I get 14. So the answer should be 13 over 14. A quicker way of getting this would have been to do what we learned earlier, namely any common factor from any numerator with any denominator in a multiplication problem can be canceled. So the 3 goes into 21 7 times, 2 goes into 4 twice, 2 goes into 26 13 times, 1 times 13 is 13, 2 times 7 is 14. So the answer to part A is 13 over 14. Now let's go and see if we get 13 over 14 for part B. Part B starts out kind of nice, because basically all we do in part B is we can reduce this to lowest terms. See, the 3 here cancels with the 3 here. The 2 here cancels with a 4 here to give me a 2. So the first term simply reduces to 1 times 1 over 2 times 1. That's 1/2. The second term, the 4's cancel, and so I get 3 times 1 over 1 times 7, which is 3/7. When I'm dealing with halves and sevenths, the easiest common denominator is 14. 2 goes into 14 7 times. 7 times 1 is 7. So the first one is 7/14. 7 goes into 14 twice. 2 times 3 is 6. So I have 7/14 plus 6/14. That, of course, is 13/14. So the answer still checks. Okay? Now, problem number 8 is designed to show you that just as with whole numbers, when you divide, you have a problem if you change the grouping. In other words, whereas multiplication does have the associative property, division doesn't. So problem A says, write as a common fraction in lowest terms. Part A tells you 8 ninths divided by 6/7 divided by 2/7. And part B says 8 ninths divided by 6/7 divided by 2/7. As I said that, didn't A and B sound alike? See, what makes this thing different is the parentheses. In part A, the grouping says, look, start with 8 ninths and divide that by 6/7. Then whatever answer you get, divide that answer by 2/7. Part B says, remember, look at the parentheses, divide 6/7 by 2/7, and whatever answer you get, make sure that 8 ninths is divided by that answer. See, here you're going to do this first, then this. In part B, you're first going to do this, then this. So let's do that. Let's do that. See, how do I divide? I leave the first factor alone, change the division to a times, and invert the second factor. So this is going to be 56 over 54, which I could simplify now, but why bother? You see, I can always simplify this, but there's an outside chance that maybe when I do the next part, I'll even have more factors that will cancel. It doesn't happen to happen in this problem, but I just want to show you that technique anyway. See, I'm going to take this number and divide that by 2/7. How do you divide by 2/7? You multiply by 7 over 2. See, to divide by a fraction, you multiply by its reciprocal. So I have what? 8 over 9 times 7 over 6 times 7 over 2. By the way, once I have this, I can now remove the grouping symbols, because once everything is stated in terms of multiplication, multiplication is associative. So now if I want, I can say what? The 2 in the denominator cancels with the 8 in the numerator, leaving a 4. The 4 in the numerator, I can take a 2 out of that. The 2 also cancels with a 2 in the denominator, leaving me a 3. Okay? And I take this whole thing. 2 times 7 is 14. 14 times 7 is 98. 9 times 3 is 27. So the answer is 98 over 27. That's in lowest terms because the only prime factor of the denominator is 3, but the numerator isn't divisible by 3. How do I know the numerator isn't divisible by 3 without even going any further? Because 9 plus 8 is 17. 17 is not divisible by 3. And a number is divisible by 3 if and only if the sum of its digits is divisible by 3. Part B says what? Same problem, only now you're going to work with 6/7 divided by 2/7 first. Well, see, how do you divide 6/7 by 2/7? You leave the 6/7 alone, change the division to a times, and invert the 2/7. So it becomes 6/7 times 7/2. The 7's cancel. 2 goes into 6 3 times. By the way, that's interesting. You notice this whole thing reduced to 3? Look at why. There was a common denomination here. You have 6/7 and 2/7. How many times bigger is 6 than 2? 3 times bigger. See, 6 of anything is 3 times bigger than 2 of that same something, so you should expect that 6/7 should be what? 3 times bigger than 2/7. But one of the beauties of mathematics is that even if you don't suspect it and don't even think it's going to happen, the mathematics comes out and does it for you anyway. So now we have what? 8/9 divided by 3, which is the same as 3 over 1. How do you divide by 3 over 1? You multiply by 1 over 3. So we leave the 8/9 alone, change the division to a times, and we invert, okay? And then we get what? 8/9 times 1/3 is 8/27. 8/27, okay? All right, let's go on. Here's one similar to one that we did in the lecture. An object travels 4/5 of a mile in 2/3 of a minute. What is its speed in miles per minute? Part A. And part B says, what is the speed in miles per hour? And again, this is a very easy problem to do if we do it mechanically. In fact, I'm going to show you how much easier this problem is to do mechanically than to do the logic way. See, we want what? Miles per minute. That means we're going to take the number of miles, which is 4/5. Per means divided by, and the number of minutes is 2/3. So the arithmetic simply says what? 4/5 divided by 2/3, and the label will be miles per minute. 4/5 divided by 2/3. How do we divide? You leave the 4/5 alone, change the division to a times, invert the 2/3 to get 3/2. 2 goes into 4 twice, so you get 6/5 miles per minute. Again, if this bothers you, 6/5 of a mile per minute is the same rate as what? 6 miles per 5 minutes. In other words, this is per 1 minute. If I times this by 5 and this by 5, you see a rate of 6/5 of a mile per 1 minute is the same as 6 miles per 5 minutes. See, this sounds like a fraction, this sounds like a whole number, but who cares? The answer is 6/5 of a mile per minute. How many minutes are there in an hour? 60. So if you go 6/5 of a mile every minute, in an hour you're going to go 6/5 of a mile 60 times. 6/5 of 60, see 5 goes into 60 12 times. 12 times 6 is 72. So this may sound a little bit funny to you. How can you be going 72 miles per hour when you're going 4/5 of a mile in 2/3 of a minute? And the answer is, even though 4/5 of a mile isn't a very big distance, you see, 2/3 of a minute is a relatively short period of time. There are 90 of those in an hour. So you're going 4/5 of a mile 90 times. But at any rate, that should give you a feeling for the problem. Let me show you, by the way, how the logical way works out. And just to show you how much more difficult it is in terms of the conscious thought process you have to go through. See, if you can do 4/5 miles in 2/3 of a minute, see, 2/3, in 1 minute you're going to do, in 1/3 of a minute, you're going to do half of what you do in 2/3. So 1/2 of 4/5 is 2/5. And if you go 2/5 of a mile in every third of a minute, since it takes 3/3 of a minute to make a whole minute, you're going to go 2/5 of a mile 3 times in 1 minute. And 2/5 times 3 is 6/5. So the answer still comes out to be what? 6/5 of a mile per 1 minute. But do you notice how much more thinking you have to do that way? See, if you really learn what I'm trying to teach you, if you have a math aptitude, great. The shortcuts will suggest themselves, and the more logical forms will suggest themselves. If you don't have a mathematical aptitude, thinking of fractions in terms of whole numbers will give you a much better chance to understand the plausibility of your answers than by doing it by another method. Well, anyway, let's get on to the last problem, which is a unit pricing problem only without price. I want to show you how we often try to do things by seeing what happens to a unit. And based on what happens to a unit, we then determine what happens to other units. See, I'm going to draw a map to scale. And the problem says a map uses a scale of 1/8 of an inch to represent a distance of 50 feet. And don't be confused by this. Some people say, how can you do this? Aren't there 12 inches to a foot? That's only for a true length. What we're saying is, here's a distance, great big distance, we want to draw it on a piece of paper. So we say, okay, every 50 feet of true distance is going to be scaled to down to 1/8 of an inch on our map. So every 1/8 of an inch represents 50 feet. Part A says how many feet distance will be represented by 1 inch, and Part B says how much will be represented by 3/5 of an inch. And in real life, you're usually told to do Part B without being given Part A. In other words, in most real life situations, what will happen is you're looking at the map, and here's point A and here's point B. You take your ruler and you measure the distance between point A and point B, and you find that it's 3/5 of an inch. Now you look for the scale on the map, and the scale says every 1/8 of an inch is 50 feet. So you now have to figure out, okay, if 1/8 of an inch is 50 feet, how many feet will 3/5 of an inch be? Do you understand that type of a problem? And I want to show you how you think whole numbers to solve this. What you're going to do is, instead of fooling around with 1/8, fool around with a whole inch, because that's easier to handle. See, if every 1/8 of an inch is 50 feet, won't 2/8 of an inch be 50 feet twice, or 100 feet? And 3/8 is what? 1/8 3 times? So 1/8 is 50 feet, so 3/8 will be 50 feet 3 times. So as you count by eighths, notice that the distance that you're representing counts as the multiples of 50, doesn't it? Do you see that? See, 1/8 is 50 feet, 2/8 is 100 feet, 3/8 is 150 feet. The whole inch is 8/8, isn't it? 8/8 is a whole inch. So 8/8 is what? Each eighth is 50 feet. So 8/8 is 50 feet 8 times. That's 400 feet. So there are 400 feet per inch, okay? 400 feet per inch. See, feet per inch is feet divided by inches, all right? Now, here's the trick. If 1 inch represents 400 feet, what's 3/5 of an inch? See, 3/5 of an inch means 3/5 of 1 inch. So whatever 1 inch represents, 3/5 of an inch represents what? 3/5 of whatever 1 inch represents. So to say I want 3/5 of an inch says I'm taking 3/5 of 400 feet. 1/5 of 400 feet is 80, so 3/5 would be 80 times 3, which would be 240 feet. In other words, 1/5 of 400 feet is 80 feet, right? So 3/5 would be 1/5 3 times. That would be 240 feet. Suppose you wanted to do Part B without having done Part A first. I want to show you it can be done, but that it's slightly more thought-oriented. See, to do Part B without A, what you may want to do is find out how many times 1/8 inch is in 3/5 of an inch. After all, how did we do Part A? Didn't we see how many eighths there were in a whole inch? But that was easy. There's what? 8/8 in a whole inch. How many eighths are there in 3/5 of an inch? That's a little bit tougher. See, what we're saying is, if you count by 1/8, when will you come to 3/5? But don't worry about that. Work it out this way. See, how many eighths? See, how many times must you take 1/8 to get 3/5? That looks like a multiplication problem, but it's what? A division problem. And it's what problem? 3/5 divided by 8. That's 3/5 times 8 over 1. That's 24/5. That's 24/5. And 24/5, you see, every 5/5 makes up a unit. So 24/5, 5 goes into 24 almost 5 times, right? It's 4 with a remainder of 4. So there are approximately 5 1/8 in 3/5. But we're not going to pursue that much further right now. We may in a little while look at that. So basically what we're saying is in 3/5 inches, we have 1/8 of an inch 24/5 times. In other words, we have 50 feet this many times. 50 times 24 over 5, 5 goes into 50 10 times. 10 times 24 is 240. So there's the same answer, 240 feet. You see, and a quick estimate would be, roughly speaking, how many 3/5 are there in 1/8? About 5. So you'd expect that 3/5 of an inch would represent a length that was about 5 times as long as 1/8 of an inch. And since 1/8 of an inch represents 50 feet, 5 times that would be 250. So without even knowing the exact answer, you'd say what? It's around 250 feet, and 240 certainly qualifies on that. By the way, I usually like to close after I've done the last problem. There is something I would like to reinforce with you in terms of vocabulary. When I say to you, take 1/2 of 8, a lot of students will convert that into a division problem because they say, when you take half of something, aren't you dividing? Here's where I want you to pay attention to language. When I take half of 8, I'm multiplying 8 by 1/2. See, 1/2 times 8 means 1/2 of 8. What I am doing is to multiply 1/2 by 8 is the same as dividing 8 by 2. You see, to multiply by 1/2, you're dividing by 2. It's a different problem. See, the tricky part is when you start taking fractional parts of a fractional part, what do you subconsciously start to think of? A part of a part suggests the word division. And that's tricky, because when you take a part of a part, that's multiplication. And division is nothing more than a multiplication problem where one of the factors is missing. Please try to think things through from that particular point of view. Everything seems to go wrong when we try to memorize fractions. Why? Because when you multiply 2 whole numbers, you expect the number to get bigger. But when you multiply 2 fractions, since you're taking part of a part, the correct answer is going to be what? Smaller than the factors. When you divide, you think of things getting smaller. But when you divide by a fraction, the thing gets bigger. See, this is tricky. 12 divided by 2, maybe I ought to write it down here, I don't know. Can we get that? 12 divided by 2 is 6. But if I take 12 and divide that by 1/2, see, 12 divided by 1/2, how do you divide by 1/2? To divide, you multiply by the reciprocal. And suddenly, see, 12 divided by 2, that checks with our intuition. The answer comes out to be 6. It's smaller. But what happened with 12 divided by 1/2? The answer is 24. Why did that happen? Because 12 relative to 1/2 is 24 times as big as 1/2. See, think of it in terms of money. See, how many $half does it take to make up $12? Every 2 $half give you $1. So for $12, you're going to need 2 halves 12 times. That's $24. So don't be tricked into a pseudo-language problem. Think the concept through. It's worth taking an extra little while now before you go on to Module 6. Because what you're going to find is, if you have mastered Modules 4 and 5, 6, 7, and 8 are almost going to seem like free prizes. At any rate, I've droned on long enough for today's session. We're going to meet again. When we do, we're going to be discussing Module 6, which deals with a new concept called mixed numbers. Until that time, continue to have fun, work hard, stay young. Look forward again to seeing you soon.